This is a contribution to the virtual workshop on Ricci and scalar curvature on the occasion of Misha Gromov's 75th birthday. My name is Bernhard Hanke. I'm based at the University of Augsburg, and my talk will be about scalar positive immersions. This is joint work with Luis Florit, who is based at IMPA in Rio de Janeiro. First of all, I would like to thank the organizers, and in particular, Christina Somani, for giving me the opportunity to talk and for setting up this interesting workshop. I think it gives a very fascinating panorama of recent developments in the fields of Ricci and scalar curvature geometry. As a gentle start, I quickly recall the definition of scalar curvature for a Riemannian manifold V with Riemannian metric G. We pick a point P in this manifold, and for some epsilon, look at the epsilon ball around P in V with respect to the Riemannian metric G. Now I can compare the volume of this ball with the volume of a corresponding ball in Euclidean space with respect to the Euclidean metric. Letting epsilon go to 0, we can write down a Taylor expansion of the quotient of these two volumes, which leads to this formula. And the coefficient of epsilon squared in this expansion is by definition the scalar curvature of G at P up to a normalization constant. In order to get some intuition, what kind of geometric property is measured by this invariant, we look at the cases of spherical, Euclidean, and hyperbolic space. So these are the three model geometries. In the spherical case, the volume of such a ball is smaller than the corresponding volume in Euclidean space of the same radius. Hence, the scalar curvature is positive at the point P due to this minus sign here. Then in Euclidean space, these terms vanish, and correspondingly, the scalar curvature is equal to 0. In hyperbolic space, we get negative scalar curvature by a similar argument. Notice that when we start with a differentiable manifold V, it is always possible for a chosen point P in V to construct a Riemannian metric such that around the point P, the geometry looks like this, this, or this. This means that locally, the condition to put a sign on the scalar curvature does not give any additional restrictions. The problem becomes more interesting when we ask about global properties, in the sense that we ask about fixing the sign of the scalar curvature globally on V. It is well known that if V admits a spin structure, meaning that V is orientable and the second Stiefel-Whitney class of V vanishes, then there is an obstruction which comes from spin geometry and the analysis of the Dirac operator. This is the topic of some other talks during this workshop. What is important for us here is that if V admits a spin structure and the so-called alpha invariant of V is non-zero, then V does not admit a metric of positive scalar curvature. The alpha invariant is a refinement of the A hat genus, which is a certain characteristic number of V. And now this theorem of Gromov and Lawson and Stolz says that in fact the converse is true. The spin obstruction is the only obstruction to global existence of positive scalar curvature in case the given manifold is simply connected and of dimension at least 5. This is a fundamental classification result in positive scalar curvature geometry. In particular, if V does not admit a spin structure, meaning that the second Stiefel-Whitney class is different from 0, then V always admits a metric of positive scalar curvature. And in the spin case, this is the only obstruction. Now, this theorem deals with intrinsic Riemannian geometry in the sense that we are looking at abstract Riemannian metrics on a given manifold. In my talk, I will concentrate on an extrinsic counterpart of such a result. The basic definition is as follows. We call a smooth immersion f of v into Euclidean space of dimension capital N scalar positive if the induced Riemannian metric gf on v has positive scalar curvature. Now we can ask if v admits a scalar positive metric in an abstract sense, for example, using the previous theorem, can we also realize such a metric by a scalar positive immersion into Euclidean space? Of course, the answer to this question is yes. We can always use Nash's isometric embedding theorem in order to construct a positive scalar curvature metric induced by an immersion into Euclidean space, even by an embedding. This requires, in general, a dimension bound which is quadratic in n. Now our question is, can we achieve a scalar positive immersion into Euclidean space of some smaller dimension than the dimension given by the Nash isometric embedding theorem? Now, going to the other extreme, if we drop any assumption on the induced metric on V, then we arrive at Whitney's immersion theorem. It says that each smooth manifold of dimension at least 2 admits a smooth immersion into Euclidean space of dimension 2n minus 1. Here we have a linear bound in n. Now, in order to distinguish arbitrary immersions from scalar positive immersions, we have a first result. This follows, as explained in the third part of this remark, by an application of the Gauss curvature equation. Namely, if we have a scalar positive immersion f, we can compute the scalar curvature of the induced metric on V by this formula, which is based on the second fundamental form alpha f of f. The trace of the second fundamental form is by definition the mean curvature field, which is a section of the normal bundle of f along V. Now, if you look at this formula and we assume that the scalar curvature is everywhere positive, then this implies that the trace of alpha f, the mean curvature field, is nowhere vanishing. Otherwise, this side of the equation would be smaller than or equal to 0 at some point. And now we can apply Hirsch-Smale theory in order to conclude that we do actually have an immersion into Euclidean space of dimension capital N minus 1. This follows from the fact that in this case, the nowhere vanishing mean curvature field defines a splitting of the normal bundle of F, meaning that the nowhere vanishing mean curvature field splits off a trivial line bundle. And hence, by the Hirsch-Smale theory, we obtain an immersion into Euclidean space of dimension capital N minus 1. This requires this additional dimension bound, since otherwise, for example, if we look at the n sphere, which immerses into Rn plus 1, scalar positively, but then this conclusion is wrong. So we do not have an immersion into Euclidean space of dimension n of the n sphere. So we need this additional dimension bound here. But we conclude that the minimal dimension of the ambient Euclidean space for immersions in a general sense and scalar positive immersions differs at least by 1. This follows from this remark under this additional dimension assumption. Let me give a couple of examples. So these are total spaces of HP2 bundles, where HP2 is the quaternionic projective plane. take a smooth manifold Bn minus 8 of dimension n minus 8 and look at a smooth fiber bundle with fiber HP2 with total space script Vn of dimension n. In addition, I assume that the structure group of this bundle is equal to the symplectic group sp3 of orthogonal 3x3 matrices with quaternionic entries. This surjects to the isometry group of HP2. Actually, the isometry group is equal to the projective symplectic group, but for simplicity, I identify these two groups here. Now recall that HP2 admits an isometric embedding into Euclidean space of dimension 14. This is induced by the following map. We look at the three-dimensional quaternionic vector space H3. We look at the unit sphere S11 in this vector space, and taking a unit vector in H3, we can associate to it a 3x3 quaternionic matrix given by x point x conjugate. This matrix satisfies the assumption, the conditions that it's self-adjoint and has trace equal to 1. Now this subset of the linear space of the 3x3 quaternionic matrices defines an affine space of real dimension 14, which we can map isometrically to R14 by an explicit map, which sends 1/3 of the identity matrix I3 to 0. So observe that this matrix is contained in this space. This Veronese embedding, which is induced by this map, which I've given here, after quotienting out the right action of the unit quaternions, is equivariant with respect to a Lie group homomorphism from sp3, which acts on HP2 in the natural way, to the orthogonal group O14, which acts in the natural way on R14. Since this embedding is equivariant, we obtain a fiber-wise isometric embedding of this fiber bundle into a Euclidean vector bundle of rank 14 over Bn minus 8. We simply pass to the sp3 frame bundle or principal bundle of this smooth fiber bundle, and then we associate to it R14 by this representation of sp3. The total space of this vector bundle immerses into R2 n plus 6 minus 1 by the Whitney immersion theorem. Notice that the total space has dimension n minus 8 plus 14, which is n plus 6. And in addition, we can arrange that this immersion restricts to an affine isometric embedding of each fiber of this Euclidean vector bundle. In particular, we obtain a family of isometric embeddings of HP2 into this Euclidean space. But now we can shrink these HP2 fibers inside the fibers, the linear fibers of this vector bundle by a small constant. And if this constant is small enough, the resulting immersion of script V into this Euclidean space is in fact scalar positive. This argument is somewhat similar to using an O'Neill formula for Riemannian submersions. But here the situation is slightly different because we are not dealing with a Riemannian submersion. However, we can do some estimates here which are not too difficult to arrive at this conclusion. And altogether, we obtain a scalar positive immersion of the total space script Vn into Euclidean space R2n plus 11. Observe that this bound is linear in n, not quadratic. And this will be the source in general for proving the main theorem. We will see later how this works. What is the main theorem? It is stated on this slide. This is our main result. It's joint work with Louis Floret from the last year. And we are in the same situation as in the Gromov, Lawson, and Stolz theorem. Namely, we take a simply connected manifold of dimension at least 5. And if V is spin, then we also assume that alpha of V is 0. This ensures that we have a positive scalar curvature metric on V. And the conclusion is that there is a scalar positive immersion into Euclidean space of dimension 2n plus 11. In other words, we can realize a positive scalar curvature metric as it is constructed in Gromov and Lawson or Stolz by a scalar positive immersion into Euclidean space of a relatively small dimension, which is linear in n. Let us look at some examples. If we take M at least 3, then the complex projective space CPM has real dimension at least 6. So we can apply this theorem. The space is also simply connected. And we can conclude that it admits a scalar positive immersion into R4M plus 11. Now, on the other hand, we have a Veronese embedding of CPM equipped with the Fubini-Studi metric in Euclidean space of dimension m squared plus 2m. Here we have a quadratic dimension bound in M. When we compare these two results, we of course should mention that being an isometric embedding is a much more restrictive property than being scalar positive. But in any case, the Veronese embedding is also scalar positive, but we have a quadratic bound in M. Now concerning the minimal dimension for scalar positive immersions, let us restrict to complex projective spaces where M is equal to a power of 2. We know from the theory of characteristic classes that in this case CPM does not immerse into Euclidean space R4M minus 2. And by the previous argument, this implies that we do not obtain a scalar positive immersion into R4M minus 1 in this case. This is exactly the Whitney bound. Hence, for such M, the minimal dimension for scalar positive immersions is somewhere between 4m equal to the Whitney bound plus 1 and 4m plus 11. We do not know the minimal dimension for scalar positive immersions. Let me formulate a question. For a manifold V, which admits a positive scalar curvature metric and an immersion into Rn minus 1, we can ask, does there exist a scalar positive immersion into Rn? So we just add one dimension. In some sense, this is a converse to the observation that we made on a previous slide, saying that once we have a scalar positive immersion into some Euclidean space of dimension n, then there is an immersion, a smooth immersion into Euclidean space of dimension Rn minus 1 under a slight dimension bound of the given manifold. Interestingly, this question always has a positive answer. So I should say, I should not talk about a conjecture, but of a question. So this question has a positive answer by Gromov's H principle for diff-invariant open partial differential relations on open manifolds. I will say a few more words about partial differential relations later on in this talk. In particular, each open parallelizable manifold V of dimension at least 2 admits a scalar positive immersion into Rn plus 1. Yeah, so here, in fact, we apply Gromov's H principle several times. At first we see that the given manifold admits a positive scalar curvature metric, which is in most cases or in general not complete using Gromov's H principle. And we also know that the manifold V admits an immersion into Euclidean space of dimension n. And now we can apply Gromov's H principle another time to conclude that we do get a scalar positive immersion into Euclidean space Rn plus 1. This follows since the partial differential relation of being scalar positive immersion can be solved formally in this case. So we might restrict this question to closed manifolds V, and we think that in this case it is quite interesting. We do not know the answer to it, and we do not have a strong opinion if the answer is yes or no. The main tool for the proof of our main result with Louis Floret is what we call an extrinsic Gromov-Lawson-Shen-Yao surgery principle. Recall that this is a very important tool for constructing positive scalar curvature metrics on manifolds of a very general type. Namely, the classical Gromov-Lawson-Shen-Yao surgery theory says, or surgery theorem says, that if V is an n-dimensional manifold and V hat is obtained from V by surgery along an embedded sphere SD of dimension D and of codimension at least 3 with trivialized normal bundle, then the following implication holds. If V admits a positive scalar curvature metric, then also V hat admits a positive scalar curvature metric. Recall that surgery means that we remove the unit disk bundle or normal unit disk bundle around the embedded SD, which is diffeomorphic to SD times Bn minus D, since the normal bundle is trivialized. We remove this from V, and instead we attach a new manifold with boundary equal to B D plus 1 times Sn minus D minus 1. This is possible since these two manifolds have the same boundary equal to Sd times Sn minus D minus 1. We can do this in a smooth way such that V hat is again a smooth manifold. And now our theorem says that there is an extrinsic counterpart of this Gromov-Lawson and Shen-Yao surgery theorem, saying that once V admits a scalar positive immersion into Euclidean space R capital N, with this additional assumption, then also V hat admits a scalar positive immersion into Euclidean space of the same dimension. We need this additional assumption since we need to make sure, among others, that the new manifold V hat still immerses into the Euclidean space. This is not trivial, or this is an additional assumption since the new manifold V hat is topologically different from the given manifold V, because we apply this surgery step. And now, in order to study a specific case more closely, on the next slides, let me restrict to a particular case. And this particular case is the case of being D equal to 0, which corresponds to taking connected sums. So we assume that V has two components, say. V is equal to V1 disjoint union V2. And we embed the zero sphere into V1 disjoint union V2 as follows. Here is the point P, and say here is the point Q. So this is an embedded zero sphere. Now, applying surgery means we remove S0 cross Bn. In other words, we remove two normal balls around these points. These are removed. And we glue in a new handle equal to B1 cross Sn minus 1 instead. Let me draw this new handle in green. It looks as follows. And of course, in order to complete the surgery step, we need to connect the new handle smoothly to the old manifold. So in other words, we have a certain interpolation region, which I draw in red. So this manifold is equal to B1 cross Sn minus 1. Yeah, this is the case of connected sums. So V hat is equal to the connected sum of V2 and of V1 and V2. And I would like to study the extrinsic surgery for scalar positive immersions in terms of this example for the special case D equal 0. Yeah, so the more general surgeries can be treated in a similar manner, but I do not want to go into many details here in this talk. So when we look at this picture, then I already made some assumptions, namely, more specifically, I assume that around P, around the points P and Q, the given immersion is of a very specific type. It maps the ball, the normal ball around P or Q into Rn such that the induced metric on this ball is of a spherical shape. By this I mean that it looks like a spherical cap. And also then I complete the surgery by attaching the surgery handle in this direction, which is opposite of the mean curvature vector at the point. So this is a rough indication how this, this extrinsic surgery is performed. But I would like to discuss two steps of the surgery a little bit more in detail. The first step concerns the question, why can we assume that the scalar positive immersion is of this specific type around P and Q? And this will be done in step 1, which will follow on the next slide. And then the next non-trivial step is how do we construct these interpolation regions where we connect the old manifold smoothly to a surgery handle such that we stay in the scalar positive immersions. And this step is step 2, which I will discuss later on. So the blue color always refers to these small neighborhoods of the surgery region S0 in this case, or more in general SD, to a normal neighborhood of SD. In the first step for constructing the connected sum, we have to make sure that the following holds. We start with a scalar positive immersion, F0, and we pick a point P in V, which we want to use to perform the connected sum construction. Now we choose polar normal coordinates on a small neighborhood of P, where the radial coordinate is denoted by S, and the spherical coordinate omega, which sits in the unit sphere and the tangent bundle TPV, is denoted by omega. On the previous slide, I can add these two vectors here at the point P. For example, on this side, I draw the mean curvature vector, psi p, and I have the vector omega, which is tangent to the given manifold V. So by the way, here we have V1 and V2. So psi of P is the mean curvature vector at the point P. And now this proposition says that given an arbitrary scalar positive immersion, this can be deformed through scalar positive immersions in such a way that in the end, the scalar positive immersion is of a very specific type. Namely, on this normal neighborhood, it is given by an immersion which is of a spherical shape using sine and cosine function. The radius of this sphere is, according to this formula, exactly equal to tau to the -1. So this is the first step, a kind of preparation before we obtain the actual surgery. So how is this done? We actually perform the construction in 2 steps. The first step only happens in a small neighborhood of P. Namely, we can write down explicit formulas in a small neighborhood of P, which homotop the given scalar positive immersion to a scalar positive immersion of this type. This is not very difficult, but I do not want to do this here in detail. This can be done by an explicit deformation. And now we extend this local deformation, which is given on U, to a deformation defined on the whole of V through scalar positive immersions. This step is not as obvious anymore, and it uses what we call the local flexibility lemma. So this is an application of the local flexibility lemma. And before I return to the proof of our main theorem about scalar positive immersions, I would make an insertion where I explain some basic facts about jet spaces and local flexibility. And then I will return to the proof of the main theorem. Jet spaces are a basic tool, basic structure when we talk about H principles or flexibility principles in geometry and topology. Let V be a smooth manifold. We are interested in geometric and differential topological structures on V, such as curvature restrictions for Riemannian metrics, symplectic or contact structures, G2 structures, and so on. And in our particular context, we are interested in scalar positive immersions. In general, these structures are solutions to partial differential relations on V. I will define what this means on the next slides. But a basic question is, given such a structure on V, we can consider a local deformation around a subset V0 in V, for example, a submanifold or just a point. This is what happens on the previous slide. But we'll look at a local deformation through solutions of our partial differential relation. For example, local deformations of Riemannian metrics which obey a certain curvature bound locally around V0. The question is, can this local deformation be extended to the whole of V while staying in the given relation, while preserving the given restriction? For example, the given curvature bounds or the given restriction of being a scalar positive immersion. So this is the basic question which I will discuss in a little bit more detail now. What are jet spaces? Start with an open subset of Rn and look at a differentiable map with values in R capital N of differentiability order Ck. Now we can write down the kth Taylor expansion of V around some given point V, which takes this form. Alpha always is a multi-vector or multi-index, which indicates mixed partial derivatives, which are denoted by this. And the collection of these partial derivatives at the given point V is what we call the k-jet of f at V. This is simply the collection of all partial derivatives of order at most k. We write this k-jet in the form little j to the k f of V. For example, the 2-jet of this function, of the smooth function, is the 6th tuple of real numbers given like this. Here if this is the value, this is the first derivative, and this is the second derivative at the point V equal to 0. So we can do this construction in the general context of smooth fiber bundles. If we have a smooth fiber bundle X over V with fiber some smooth manifold, then we obtain an associated smooth fiber bundle, which we call capital JKX to V. The typical fiber over a point V in V of this fiber bundle is given by all possible k-jets of sections of this bundle, which are locally defined on a neighborhood U of the point V. So this makes sense in an invariant fashion, so we can do this for abstract fiber bundles, and the associated bundle is called the k-jet bundle of X. So once we have these structures, we can define the notion of a partial differential relation of order k. This is simply a subset of the total space of capital JKX. And this subset specifies relations which partial derivatives up to order k have to satisfy. This will become a little bit more clearer if we talk about solutions of a partial differential relation. Namely, we call a section, a CK section of the given smooth fiber bundle, a solution of script R of the given partial differential relation if the associated section of k-jets of F has values in the given subset script R. Examples. We can take ordinary differential equations or inequalities of order k for functions defined on open subsets of the real numbers. These define a partial differential relation of order k, certain subset of the k of the total space of the k-jet bundle, associated to the trivial fiber bundle over V with fiber Rn. An important example arises in Riemannian geometry. If we take the bundle of positive definite symmetric bilinear forms on TV, on the tangent space of V, then sections of this bundle are called Riemannian metrics. This is well known. And curvature restrictions for such metrics define partial differential relations of order 2, subsets of the jet space J2X. Now again, going back to the case of trivial bundles, meaning that sections of this bundle are just functions with values Rn. And we can define the partial differential relation associated to scalar positive immersions. We have two conditions. The first says that such a map must be an immersion. So the differential must be injective. And also the induced metric should be scalar positive, should have positive scalar curvature. And this defines an open partial differential relation, an open subset, since these two conditions are invariant under small perturbations. Now we can define what it means to talk about local flexibility in this context. Let X over V be a smooth fiber bundle. Let V0 in V be a closed subset. And let script R be an open partial differential relation in the total space of the K-jet bundle, of the given fiber bundle. Furthermore, we assume that F0 solves the partial differential relation. Now we restrict to a neighborhood U of V0 and assume we have a family of solutions of our partial differential relation over U, starting at the restriction of the given solution F0. In other words, we look at a deformation of this solution over a subset U of V, which is the neighborhood of V0. And in addition, we assume that the K-1 jet stays constant along V0 throughout the deformation. This picture indicates what's going on. And here we may think of the relation saying that the second derivative of f is positive. We could take this relation, and then f0 is a solution of this relation. So in this case, v is just the real line. To keep the picture simple, v0 is a point, and u is a neighborhood of this point. So then we have this solution f0, and we have a deformation over the subset u through solutions of the partial differential relation. In this case, local flexibility holds. This is joint work with Christian Baer from 2019. It says that there is a smaller neighborhood, U0 of V0, sitting here, and a continuous path of solutions of the partial differential relation defined on the whole of V, such that this family starts at F0, at the given solution. At any time, we have a solution of the partial differential relation. And furthermore, on this smaller subset U0, this deformation coincides with a given deformation, large F. So this is this region here. And furthermore, outside of U, outside of the larger neighborhood, the globally defined deformation stays constant. When we look at this picture and think of the partial differential relation second derivative positive, then this is slightly misleading, since we see that at this interpolation region, we do not preserve the relation. But notice that we can pass to a smaller U0 such that this relation is indeed preserved. And we also see in this picture what the difficult part of this theorem is. It concerns this interpolation region. And in fact, the proof of this theorem goes as follows. We have to construct a cutoff function near V0, which is equal to 1 in a small neighborhood of V0 and equal to 0 outside of U. And then we multiply the time parameter inside the given deformation, capital F, by this cutoff function. This will result in a family of sections in the given smooth fiber bundle, but it is non-trivial to conclude that we stay in the given relation. And in fact, if we work with an arbitrary cutoff function like this, it is relatively easy to control the k-1 jet of the resulting globally defined family. And since the given relation is open, the k-1 jet can stay in the given relation quite easily. The difficult part of this theorem concerns the k-jet, the kth partial derivatives. And for this, we actually need this additional assumption here. Otherwise, the theorem doesn't hold. And with this assumption, it is indeed possible to construct a cutoff function which proves this theorem here. But this is highly non-trivial. And it is indeed done in our joint paper with Christian Baer. So once we have this theorem, we think of the case of scalar positive immersions. And on the previous slide, I are exactly in this situation. If V0 is a point, the point P, and in a small neighborhood, U of this point, I have a family of scalar positive immersions. And in fact, we can do it in such a way that the one jet is preserved during this deformation at the point V0. And then the theorem says that automatically we can extend this to a global deformation through scalar positive immersions. So this theorem is very general and has, of course, many applications. Okay, let me go back a little in history, since this theorem has an interesting past. In his 1986 monograph on partial differential relations, Misha mentions this fact as an exercise. Under strong regularity assumptions on V0, he assumes that V0 is a submanifold. And in his GAFA paper from 2018 about metric inequalities with scalar curvature, Misha Gromov states again this theorem for V0 which are stratified by smooth manifolds. Neither in his book nor in his GAFA paper he gives a proof of this statement. So this reminds you of the book Partial Differential Relations, which I display here since I believe it is still a gold mine in our field. It has many more very interesting assertions, exercises, and theorems that are definitely worth studying in the future. Now, after having completed the first step for our connected sum construction, bringing the scalar positive immersion into a special shape around the connected sum point P and Q, we can continue with the connected sum construction. And this concerns the construction of this interpolation region, which connects the spherical region of our smooth immersion to a region where I can attach the surgery handle. So this picture has to be read as follows. Here I have the two coordinates omega again. So this is a unit vector in the tangent space at the point P. This is the mean curvature at the point P. And in fact, this curve here just indicates the what we call bending profile, though the actual manifold is immersed like this. And this is the blue region that we constructed before, the spherical region. Since this spherical immersion is rotationally symmetric, we can specify such immersion by bending profiles. Gamma, this is related to this curve here. And now we construct the interpolation region in terms of a bending profile gamma with values in R2, which we think of the plane spanned by omega and psi. A bending profile is by definition a smooth curve with constant speed. And then we can consider the compact manifold sigma gamma, which is equal to the unit sphere in the tangent bundle at the point P with some closed interval alpha beta. And here this gamma is in fact the curve drawn in red. Yeah, I look at this immersion induced by gamma. And the question is, for which gamma do we still get a scalar positive immersion? This is a non-trivial question, since this curve gamma starts with this shape, which is curved very much in case we choose this sphere, the spherical cap of very small radius. And then we end in a curve which is not curved anymore. The curvature is 0. So we have to interpolate between these two regions. But we can formulate this in terms of an ODE for gamma, which we can indeed solve. And then we can, in this way, continue with our construction of connected sums. By the way, in order to glue the red region with the blue and green region, we once more apply the local flexibility lemma. And once we arrive at an immersion which is parallel to psi p, we can indeed complete the surgery, because here we can add the surgery handle like this. So this just indicates the kind of immersion that we get using this bending profile. Yeah, and a similar construction applies to more general surgeries, but I do not want to go into details here. Those of you who know the classical paper by Gromov and Lawson in the Annals, 1980, recall a similar picture in their paper. They also have to consider bending profiles gamma. But the difference in this paper is that they study immersions or embeddings into manifolds which have positive scalar curvature. So the ambient manifold here has positive scalar curvature in their paper. In our context, we are dealing with immersions into Euclidean space, which has 0 scalar curvature. And therefore, a more refined argument is needed here. So now we have the extrinsic surgery principle at hand. And using this, we can complete the proof of the main theorem on scalar positive immersions. Recall the theorem. It says that if we have a closed simply connected manifold V of dimension at least 5, and if V is spin, also alpha of V has to vanish, then there is a scalar positive immersion into Euclidean space of dimension 2n plus 11. The proof goes as follows. In the first case, we assume that V admits a spin structure, and by theorem of Craig-Stolz, it holds that the manifold V is spin bordered to the total space script V of an HP2 bundle with structure group, the isometry group of HP2. This uses the assumptions that V is simply connected and alpha of V vanishes. Now we can use our construction from a previous slide to obtain a scalar positive immersion of the total space into Euclidean space of dimension 2n plus 11. The manifold V is obtained from script V by a sequence of surgeries in codimensions at least 3. This uses the fact that these manifolds are bordered, V and script V, and also that the fundamental group of V vanishes. In fact, we use Handel cancellation techniques coming from the proof of the H-Cobordison theorem, and these techniques were already used in the work of Gromov, Lawson, and Stolz. And hence we can conclude the main theorem from the extrinsic surgery principle, which I proved earlier in my talk. Yeah, V is obtained from script V by a sequence of surgeries in codimensions at least 3, so the extrinsic surgery method applies. If V is not spin, then we are in a similar situation, but we can actually restrict to total spaces of CP2 bundles instead of HP2 bundles. And it turns out that we, in this case, get scalar positive immersions into R2n plus 7, since the corresponding Veronese embedding has a different dimension bound for the target Euclidean space. Remarks. So we can improve our dimension bounds for scalar positive immersions using Cohen's immersion theorem. This gives a better dimension bound for the target Euclidean space for getting immersions of smooth manifolds. So this dimension bound depends on the dimension of the given manifold. So the dimension bound for the target Euclidean space. And using this, we can, in many cases, construct scalar positive immersions into the space R2n minus 1, which is exactly the Whitney bound. So in these cases, the Whitney bound is sufficient in order to obtain scalar positive immersions. Furthermore, we believe that our approach can be generalized to some non-simply connected V, but this requires additional work, which we have not done yet. So my talk is based on the following 2 references. There is the paper Local Flexibility for Open Partial Differential Relations, which solves Gromov's exercise. This is joint work with Christian Baer, and you can have a look at it at the archive. And the paper which contains the discussion of scalar positive immersions is also available at the archive. That's joint work with Louis Florid. I thank you for your patience and your attention, and would be happy to receive your comments and questions. Goodbye.